I'm very happy to present you the outcomes of my PhD program, conducted under the supervision of type systems expert Giuseppe Castagna and the renowned Giuseppe. This project was initiated 2 years ago during mail exchanges between Jose and Giuseppe, when they decided to bring on a PhD candidate to help realize their ideas. And now, after 1.5 years of work, I'm super excited to present you the type system that we've designed for Elixir. This presentation, its goal would be to showcase its capabilities and the ways it can enhance the Elixir developer experience. So let's dive in and first discuss why types. So as you know, Elixir already adds as types. In fact, you can write a function that checks the type of its input, but this manipulation only occurs during runtime, which is why we talk of a dynamically typed function. It is also possible to write type specs, but Elixir uses those mostly for documentation, and although it is possible to pass them to external tools to provide code analysis, Elixir itself does not make large use of it. And this is precisely what we want to do. We want to introduce a system of types that will be used before running your programs, before compilation, to analyze the behavior of your programs and detect bugs. And speaking of bugs, here's a simple example of the kind of bug that we want to catch. This is a function that applies a Boolean negation to something that is always an integer, and you would get a simple type error, blaming the plus operator here. In general, though, you would want to use types to annotate the behavior of your functions and to act as contracts between the input and the output that your functions produce. So an example of that would be this toy function, negate. It manipulates integer, and we would want to enable the syntax for adding a type annotation over this function. This syntax with the $sign is a type annotation, and what it tells you is that the function definition that follows, if you give it a value that has type integer, it returns an integer. Now when you use this function in another annotated function, such as subtract, which has the annotation that if you give 2 integer arguments to this function, it returns an integer. Well, this function is well typed because the negate of b does have type integer. What happens though if you modify the implementation of negate and if you add more clauses to handle other kind of data types? For example, adding a clause for booleans now means that you have to update your type annotation. And one example of a type annotation that you could write is the following one. This type annotation means that when you give a value that is either an integer or a boolean to function negate, it returns you something that is either an integer or a boolean. And this is a union type, and it has to be understood in the most intuitive meaning that if a value has type T1 or T2, then it has either type T1 or type T2. Now though, the problem is that function subtract doesn't type check anymore, because you are giving to the plus negate of b, which is an integer or a boolean. So you get a type error here, which is unfortunate tonight, because if you look at the implementation of negate, if you give an integer to negate, you're always going to get an integer back. So we want to be able to write a type for negate that is precise enough so that function subtract type checks. And we can do exactly this using a type intersection, a type intersection of function types. And this is the type annotation that we want to write for negate. Here, this type annotation tells you that negate has both the type of functions that when given an integer value, they return an integer, and when given a boolean, they return a boolean. And now, subtract type checks. Our type system also has other features that make it quite expressive to type to write type annotations for your functions. For example, here, for this example of a logical neg, which is a very simple function, its behavior is that when you give an input which is either the atom false or nil, you get true, and you can write exactly this type using singleton types, which are types containing exactly one value. Here, the false type in the annotation is a type that represents exactly the atom false. And if you want to write a type that describes the second clause of this function, whose behavior is that if you give it x, which can be any value except the atom false or nil, you can write this too, using a negation type. Here, the type not false or nil is the type of any value that is neither false nor nil. Our type system also allows you to write polymorphic type annotations. So polymorphic functions, they are functions that can do their work on many different types. And the map example is a good example of that. And here's its implementation of lists. And we can write this type annotation for it. So here, the leftmost type is the type of lists with elements of type A. And A here is a type variable. So this type, if we read it together, it is the type of lists with A. It is a function type, which when you give it a list with A elements, and a function from A elements to B elements, you get back a list of B elements. And the type variable, they're quantified after the type using this when syntax. And we can specify upper bounds on them. Here, the upper bound is just term, meaning that we do not restrict A, but we could write a precise upper bound if we wanted to restrict what A can be. The type system also performs local type inference, meaning that you do not have to specialize, to specify what A and B are when you apply those functions. For example, if you apply map to this list that contains integers and booleans, and you apply it with a function that takes a tuple and returns an integer, then the type checker, before running your program, before compilation, will see that this function application returns a list of integers. We can also combine the two, type intersections and polymorphism. So here's an example of that with this logical OR function. So if you look at the behavior of logical OR, it has two arguments. And when the first argument is either false or nil, it returns you its second argument, meaning that the return type will be the same as the second argument. So if you capture this type by a variable A, you can write this exact type. Now, if you want to write a type that describes the second clause, you can see that this second clause, when it receives the first argument, which is anything but false or nil, it discards its second argument and returns the first. So you can write the following type, where B here has an upper bound, which is not false or nil, meaning that B can become any type that doesn't contain false or nil. So having this precise system of static types means that we can improve the usability of some of Elixir features, and one of those is improve the use of protocols. So just a quick reminder, protocols, they allow you to define a set of operations to be defined on a certain data type. And the string cars example is the simplest example of that. It mandates that you implement the toString function. And one essential type, when you work with protocols, is the type of all values that implement a certain protocol. And for string cars, that would be stringcars.t. And in fact, this type, it is automatically filled in by the Elixir compiler, but currently it is approximated by term, by any type. But now we can use a precise union type to represent exactly all the exact union of all the types that implement the toString protocol. And that would include the base type, for which it is defined, strings and integers, but also some some custom types that for which you would define toString. Having this feature enables us to solve two issues of protocols. One is how to parameterize them. Can we pass a type to parameterize a protocol in particular for a specific use? And if you look at libraries that are defined on values that implement certain protocols, such as the function into, this is its current type spec. The into function, it takes an enumerable, a collectible, and it inserts the elements of the enumerable into the collectible. And currently, you do not have a way to specify what the elements of those structures are. But now we can, because enumerable T of A is the type of values that implement the enumerable protocol and which contain elements of type A. That would be a list of A elements, for example. And now we can write a precise type annotation for the into function, which is the following one, which tells you that given an enumerable containing A elements, a collectible containing B elements, you will get as a return, returned some collectible, and its elements are either of type A or of type B. Using this, and also intersection types, we can also do composition of protocols. And let me show you an example of that. You can define the custom type of traversables. They are type of values that implement both protocols and which contains elements of type A. And if you had to write a function that needs values that implement both protocols, such as this little echo function, now you can write a precise type annotation for it. So now if you apply echo to IOStream, you have a read and write loop that you have type checked a nice read and write loop that tells you back just what you said, because IOStream, because streams in Elixir, they implement both enumerable and the collectible protocol. In fact, if you look at this example more closely, we have specialized the elements inside the traversable to be strings. So we can easily add an operation on strings to the function, so that now we have type checked and a read and write loop that will capitalize everything that you give it. And this is a good application of both intersections and parametric types for protocols. Now, one key issue in devising the type system for Elixir was to handle its powerful pattern matching mechanism. And the pattern matching, it occurs both in function definitions and in case expressions, which is why those two function definitions are equivalent. In fact, pattern matching in Elixir, it gives us already a wealth of typing information. And we can leverage that to provide more precise types and to give some good feedback on your code. And let me show you how. So this result type definition, it defines result, which is a kind of map which has two fields defined. Its first field is the field output. And if output is set to the OK atom, then there will be a second field, which is socket, which contains a value of type socket. And if the field is set to error, then you will have a message field defined with inside either a timeout or a topple with the atom delay and an integer. Now, if you write a function that handles this kind of result value, you would write, for example, this one, and you would pattern match on what the values inside of the fields are. And here, if you pattern match on our output is OK, and then on our message when it is timeout, what you see is that you are going to miss the cases where the result is something where the field is set to error and you have a tuple. And the type checker would give you here a type warning saying that this pattern matching is non-exhaustive. And it would output you, it would compute for you the precise type of the values that escape your pattern matching in all cases. Similarly, if you were to change this code and now correctly pattern match on OK, then on error, and if you were to write a third clause here that wants to do something when there's a socket inside of your result, well, this third clause is already matched by the first one, meaning that this is an unused branch, and you would get also a type warning pointing out at the exact branch that is never going to be considered, never going to be entered. This wealth of typing information inside of pattern matching means that the type checker usually can compute the exact type that one of your functions will return. And here's how we can leverage that by using this notation, result to underscore. This is a way to say that you just specify the input type of your function, and then you let to the type checker the goal of computing the exact result type that you get. And here, that would mean that in the first clause, the type checker looks at our output being matched to OK. So it knows that our socket is something of type socket. In the second clause, when you check that our message is an atom, it means that it is the timeout atom. And in the third clause, which matches the rest of the values, it knows that message must contain a tuple. So this will be typed lm. The second element of our message will be typed as an integer, meaning that you get the return type computed for this function as this union of all the types possible when considering all of your branches. In fact, the type checker could infer the even more precise intersection type that follows, and that gives you the exact return type for every possible input type, as long as it is a subtype of the one that you specified for the input. One key issue was also to devise a syntax to represent map types. And here's how we do it. So this is an example of type T, which represents a map, which has a foo field set to atom. It has an optional field bar set to an atom, if it is defined. And then any other atom field would have to be defined to an integer. And here's how then we are going to type check the access to this map to a program, to M if it is of type T. M.foo will be typed with the type atom. But if you try to access the field bar, you would get a type error, because the dot access in Elixir means that the key has to be defined inside of your map. There's, however, another way to access maps whose field may be undefined, and that's the bracket notation. And in that case, we would type M bar with the type atom or nil, because you will get nil in the case where bar isn't defined. If you try to access any other atom, such as other, you would type it with the type integer or nil, because that follows the type specification. And then, finally, if you try to access an integer field, this would be typed with the type nil. And possibly you would get a type warning here, because you're trying to access a field that would never exist. So, adding types to Elixir means that we have to take into account that a large part of the code is already written. In fact, all of the code is already written. So to address that problem, we adopt the strategy of gradual typing, which means it is a way to blend statically typed and dynamically typed code. And for that, we introduce the dynamic type, which is a type that can become any other type at runtime. So we offer a relaxed type safety guarantee that tells you that if some of your program E that does some computation as type integer, then if this program evaluates the value, then this value should be an integer. One issue with using dynamic, which has been used in popular languages such as TypeScript, is that the dynamic can go through your type annotations and not take them into account. Let's take an example here with idweek, which is the identity function. Here, this annotation is good, right? Because if you give an integer to id week, you get back an integer. And if you apply id week to something that is dynamic, the only thing you can say is that the return of this function has type dynamic too. Because you could give a Boolean under the guise of dynamic, and you would get a Boolean. However, if you look at this second function, id strong, it is the same, but it checks the input, the type of its input. Meaning that now, if you apply id strong to something of dynamic, you know that if something is returned, it will be an integer. So we call that a strong function type for id strong. And a strong function type is a function type that outside of its domain, it's going to fail on a type error, or it's going to give you a value which is inside of its codomain. And here the codomain is integer for id strong. That makes us able to give a strong guarantee on the types that strong functions output. And we do that without modifying at all the Elixir compilation, because we take into account what is already being performed by the Elixir runtime. In fact, our type checker can do something more specific. If you look at this function, negate, and you type check it in a dynamic typing mode, meaning that you don't write an annotation, so its input is assumed to be something of type dynamic. Well, you could say that this function checks its input, and it's always going to return something that is either an integer or a Boolean. But if you did that, then if you try to apply this function inside of subtract, you get a type error possibly, because you gave something that is either an integer or Boolean to plus. Well, we don't want to do that in dynamic typing mode. So instead, we give, as a result type for negate, this more precise type. This is integer or Boolean intersected with the dynamic type, which means that the function negate can return something that has to be lower either an integer or a Boolean, but it could be always an integer, or it could be always a Boolean. And this relaxed way of type checking allows us to type check subtract with type integer, knowing that if a Boolean is given there, you will get a clear type error. However, if you give the result of negate to, for example, the concatenation operator, you will get a type error because it is not possible that this application succeeds. So, to sum up what we've been doing, we've been working on the formalization of complete type system for Elixir. We've defined a syntax that I've shown you a few examples of that. We've also implemented a prototype to type check our specific examples on which we conducted our research. And as this presentation ends, we've now presented our design choices to the community. Our next step will be to publish our approach. And in the second semester, we'll work on the implementation to bring that to the Elixir compiler. If you're very interested in more details, you can find at my academic page a draft of our paper about the Elixir type system, and it will give you much more explanations about everything that I showed you in this presentation. I also spoke of a prototype, and if you want, you can play with it. It is only for the conference, the people who come at the conference. It is very experimental. It is only to type check the examples that we've been developing the research on. And it is not something that is a user product. It is just, if you're curious about what we're doing, you want to interact with us and give us feedback, you can play with it. And that's all for me. If you have any questions, I'll take them, and possibly I'll redirect them to my PhD advisor.
Remind people to not share the UI.
Please do not share these URLs.
Okay. So unfortunately, we don't have time for Q&A. No, joking. Okay, who has any questions? Here, raise your hands. Okay, I'm going to start from closest to farthest.
I had a question about the negation types specifically. What was the decision making around wanting to add those versus being explicit about what types are allowed versus ones that aren't allowed in terms of return and input?
So the negation type, the negation type is something that is even more expressive. It is a new type that allows you to take any type and say, I want only the values that are not at all in this type. So if I understood your question correctly, it is because it is something that is more expressive, and that also it comes with the original theory that we are using, which is the idea of seeing types as sets, meaning that if a type is in ID the set of all the values that have this type, like integer is the set of all of 0, 1, 2, 3, then you can take two types and say, I want the intersection of this type, T1 and T2. You can say, I want the union of these two types, T1 or T2. And you can say, I want any value except the ones that are inside of this type. And Jose, do you want to add something too?
Not false or true?
I have too many slides.
Yes. So, in this case, you need the negation because it will be impossible to explicitly say everything else that does not go there. Yeah, so in this case, we have not false. So the question is like, well, maybe we don't need not. But not saying, well, you're going to have all the atoms which are infinite. So you would have to list all the atoms which are infinite. And you would have to list integer, list, map. So the negation is just very convenient because describing infinity would be hard.
And I can give the theoretical answer is that we don't need intersection because they are encoded by De Morgan laws with union and negation, and to check subtyping, so when one type is containing to the other, well, S is smaller than T if S intersection not T is empty, so all our algorithms work checking the emptiness of all these types. So you need also from a theoretical point of view.
Thank you.
That's 3 answers for each question.
Does this answer a question, by the way?
Hi, thanks first of all for sharing your findings, really interesting. I have a question. Do you have any plan for type checking regarding Elixir structs?
Yes, in fact, structs in Elixir, they are maps. So we already type check them perfectly with a map type, which has the struct field defined to the name of the struct. Yes. Do you want to go there?
No.
Okay. Hi, I'd like to know how would you be able to also type check Erlang dependencies?
Sorry.
Erlang and Erlang dependencies, so you could also see how your dependencies would influence your code, like the types, how it would influence your types, the Erlang dependencies.
Well, you're talking about adding type signatures to some foreign code, right?
Yes.
Foreign libraries. Well, in that case, I think you would have to write interfaces manually that specify what kind of input and return you expect from those foreign interfaces.
Make it a good one.
About specifically type checking Erlang code, well, our work is Elixir is similar to Erlang, so it applies to it, but this is not something I've specifically worked on. But this is once you have a static type system, those kind of things become possible to write interfaces and take them into account.
Yeah, just one parenthesis on the struct. When it comes to the implementation, our mindset right now is to first start working with patterns and guards, because, as Guillaume said, there's a lot of information in guards already. We know we can extract a lot of information from that. But the other thing that we have in patterns are structs. And structs usually match on the name, but all the struct fields, they may have type information. So like the user name is going to be a binary. And that information right now is not carried through the system. So it may change, but right now what we are thinking when it comes to the implementation is that we are going to focus on patterns and guards. And then the next thing we are actually going to type. And when we start typing patterns and guards, you won't have to change your code. It's just going to work because the patterns and guards are there. And most likely, the first contact that we are going to have as developers with the new type system is going to be through typing structs. So it's likely that you're going to be typing a struct and adding types to struct fields before you add types to functions. That's the mindset right now, but we'll see how it goes. But that's, yeah, where we are.
All right, I think we have time for one final question. I see a gazillion hands up.
Yeah.
Sorry. So I'm just going to choose the closest one. I'm sorry. So
Overrun a little bit?
I'm sorry. Overrun? Even yeah, but we are officially already overrunning. Okay, let's see. Let's see how it goes. So you raised your hand.
So, if I'm not wrong, currently Elixir LS can get some typing information from type specs, and so introducing this new syntax can be gradual. I add new things to my Elixir code base. But what is the strategy of migrating from type spec annotations to those new annotations?
I think this is a question for Jose.
Nice one. Nicely dodged.
Yeah, so they will both coexist for a while, potentially forever, because I don't think type specs are going anywhere because of Erlang. So they are going to coexist, but the idea is that because if this works out, right, it's important to put that condition. If it's working out so far, but there's still a lot of work. But if this works out, it's going to be much more integrated with Elixir. And today, during my keynote, I said we have the code fragment, which is we are working on the tooling for IDEs. So when it comes to the Elixir language server folks to implement those features, it's all going to be coming directly from Elixir and will be more integrated in this aspect, or try to be more integrated in IEX and all this kind of stuff, and try to have more visibility of the types to the developer.
All right, so to make it a little bit more fair, I'm going to walk this side all the way back. So.
So when it comes to structs, and you mentioned weak versus strong, was it signatures, or what was the word you used?
Strong function types.
Strong versus weak function types. When it comes to, from the example at least, you showed that for the function type to be strong, you had to match with a guard on every single sort of condition on the type. How does that intersect with or interact with structs, where a lot of the time you only match on, say, the name of the struct, and then a lot of sort of information comes in through that theoretically, but you don't actually match with a guard, because I don't know, because then it would have to sort of check the types that get set in the struct and when they get pulled out, or I don't know, that was a general question, but did you understand the gist of it?
Yes. Yeah, definitely. So your question is, if we pattern match on a struct, is that strong?
Yeah, more or less.
Well, yeah, it is, because I think that Elixir is then going to specifically check if the struct of this map that you get as input, which is a struct, is defined. And possibly it could check some more if the struct definition allows to specify some type inside of it. But I guess this would be an extension, something different.
So
just come on. Sorry.
yeah, so the idea, and you may have to correct me, but the idea, we are going to automatically check if, where are you, Hans? Yes. We are going to automatically check if the function is strong or not. So for example, if you have a struct and you don't have any guard on the struct fields, so the rule for strong functions, it's clear, is that, so if you look at the arrow, the domain is the left side of the arrow, and then codomain is the right side of the arrow. So if we
There's an arrow.
yeah. So if we pass something that is not the domain, if we negate the domain, and it either raises or returns the codomain. So looking at this example here at the bottom. So let's say, well, what happens if ID strong, is that what's written? Yeah, ID strong. So if you pass something that is not integer, like a Boolean, does it return an integer or fail? In this case, it's going to fail. So it's like, oh, it's a strong function. The type check is going to check that for us. So in the struct case, it may be or may not be strong, because depending on the operations that you are doing. So for example, depending on the operations that you are doing, we are going to figure out, oh, okay, yeah, we can see that this rule is applying. We are passing something that is not a struct, like if we say like the field is a binary, and then when we type check it with the field not being a binary, it raised them like, oh, okay, yeah, it's this strong. But yeah, so the idea is that this is not the concept of being strong. It's like, it's very important, and we are very proud because it's like new theory for gradually typed languages. But the hope is that as developers, we won't have to worry about it. It's just going to be there, and it means the type system is going to do what we expect even when we are intersecting static and dynamic code.
Awesome. Hi, Guillaume. Thanks for presenting your research. I think it's really exciting, and yeah, it could be transformative for the Elixir language. My question is, so I was working with TypeScript a bit, and in TypeScript you have some more advanced types where, for example, if you have a map with a specific set of atoms, then you can define a type that is basically a union of all of those possible atoms. So is that something that you thought about, given any thought, or is that just syntactic sugar that we built on top of what you presented?
This required a significant extension to the theory be that types maps, specifically this, being able to do that. And that was that the gist of your question, I think?
Asking if you already worked on having that and being able to create a union type like that.
So what is the feature?
The feature is talking about is being able to specify the type of any other atom except bar and field. This is a very specific extension to typing of maps.
Yeah, and the question is if it works, and yes, it works.
And yeah, it works. Oh, sorry, yeah.
The answer is yes.
It is, if you are very, very curious, this, no, maybe it will appear in the paper later.
A couple of days.
Yeah.
Like maps were actually the hardest part of the work so far, right? Do you agree? Yeah. So, but yeah, yeah, that's what Guillaume is saying. Like we have that, but it was lots of work. It doesn't look like that, but sometimes we'd have 3-4 hours meeting just talking about maps and how to type them. So. Yeah.